in this project, in this thesis work, we have created an antibacterial material consisting of cellulose nanofibrils and dendritic polymers. But why did we do this? The antimicrobial resistance is one of the biggest threats we face in our society today. It was estimated in 2019, there was over 1.27 million deaths related to antimicrobial resistance. And as you can imagine, this is mostly going to affect regions with low income. And as a result, it would mean that we will even have a bigger divide within our society due to this. So this is a huge problem. This comes from the misuse and overuse of medicines such as antibiotics. We know that we are overprescribed them sometimes, and we don't use them properly. We don't know how to use them properly. So the World Health Organization identified these pathogens as some of the top ones that we need to focus on, because they've shown numerous times that they do tend to form a resistance towards multiple antibiotics. And also, it also shows that if we are going to develop an antibacterial material, it needs to tackle both gram-negative and gram-positive bacteria strains. But what are some of the current solutions that are out there? Some are to move away from the conventional antibiotics and go towards cationic polymers. But specifically, we will focus on dendritic polymers. Dendritic polymers I will describe in a minute, but they are highly branched molecules. These are some of the examples of the dendrimers that have shown to be active towards both gram-negative and gram-positive bacteria. What's actually been shown by these bacteria, by these dendrimers, for example, the PAMA, is that the cationic nature of these dendrimers interact with the negative surface of the bacterial membrane, causing it to disrupt and eventually leading to cell death. But the challenge is, there's always challenges. As you develop antibacterial material, you also have to think about cytotoxicity. This is how viable are they with human cells? Are our cells able to survive in their environment with these antibacterial materials? And the challenge is that same cationic nature that provides the antibacterial property is the same one that is also thought to disrupt our human cells. So this is a problem. And one of the ways that we can slow down the potency of our antibacterial materials is by using hydrogels. If we can incorporate the active compounds within the hydrogels and use them as delivery system, maybe we can slowly release the active ingredient and thereafter decrease the cytotoxicity. So the aim of this work was to develop a new platform of antibacterial hydrogels that are based on cellulose nanofibrils and dendritic polymers. But the one other goal was to showcase the capability of cellulose. This is a raw material that is derived from wood, and we want to show that it also has a space in the biomedical field. We need to start using this in all kinds of fields. So in the next slides, I'm going to talk about in detail the dendritic polymers and thereafter describe to you what cellulose nanofibrils are. Polymers come in different shapes and sizes, but the ones we focus on are in the branched family. This is where we find dendrimers and dendritic-linear-dendritic block copolymers, which I will refer to as DLDs. Dendrimers are perfect structures. They are monodispersed. That means there's only one compound when you have only one structure with one molecular weight when you have a monodispersed dendrimer. The amazing thing about it is that it's multivalency, where it has a high amount of functional groups decorated on the periphery. So in comparison to the linear polymers, where it's a coil and the functional groups could be intertwined within the coil, this is actually on the surface. So they're able to access, they're easily accessible. On the other hand, we have DLDs, which contain both the linear polymer and dendritic part. These are polydisperse. So we use for example, in this project, we use polyethylene glycol, the polydispersed version of it, sorry. The reason why we do want to use DLDs is that they are a more simplified synthetic approach. So this way, we have structures that are monodispersed and polydispersed, and now we have a library of different characteristics of compounds. Moving on to cellulose nanofibrils, which I will now refer to as CNFs. These are nanoparticles that are typically derived from wood and plants. They are abundant and renewable, but the properties that are most attractive in this project was their high elastic modulus and their ability to form hydrogels at very low concentrations. The preparation of CNFs in this project happened by first pre-treating the pulp by oxidizing the pulp using a catalyst called TEMPO. This is one of the most commonly used methods in the process of preparing CNFs. We then subject the pulp, the chemically modified pulp, subjected to disintegration, mechanical disintegration, which then leads to liberation of the fibrils, and in turn, we can then make low concentration dispersions. But why did we take these two platforms together? Why did we think, let's put these two things together? It's because together, they actually provide us with the material of the desired properties. We get the antibacterial functionality from using dendrimers that, again, like I said, they have a high valency, so we can functionalize them with ammonium groups, which we know that have shown to be active towards both gram-negative and gram-positive bacteria. We've chosen a skeleton that is polyester-based. We use a monomer called bis-MPa. This is a very cheap monomer. It is readily available, and it is the perfect monomer to make our polyester dendrimers, and eventually they would then be biodegradable. And then when we think of but because I mentioned that because of the ammonium groups, we will also have a cytotoxicity related to these compounds. So that's where our CNFs come in, because no matter what you want, you will never form a hydrogel with just dendrimers by themselves in solution. We need CNFs, because these have the capability to form hydrogels. The CNFs, I didn't mention in the before slide, is that they actually decorated, after we prepared them, they're now decorated with carboxylate groups. And these two, the charged dendrimer and the CNFs, can electrostatically interact to form our hydrogels, which have over 99% water. And this is unbelievable, because if you think about it, we have a material that you can hold, and it's over 99% water, and it's also antibacterial. So we actually have something quite incredible here. I'll now talk about the different projects. So the first project was more the screening. This is the first time we realized what these materials could do. We put a degradable cationic dendrimer, which is, I'll describe later, but it's the beta-alanine. It is also a polyester dendrimer. And we saw that when we put them on top of a CNF dispersion, we can form a hydrogel, and they were also antibacterial. So with this in mind, we then expanded the dendrimer library by including dendrimers that have a higher hydrolytic stability, as well as DLDs. Dendrimers and DLDs to expand this library, because we think, okay, these are really interesting molecules. Let's make sure we have more of them with different characteristics. And in project 3 and project 4, we then form hydrogels separately. In the third project, we formed the hydrogels with the dendrimers and compared and contrasted them, their biological activity. And in the fourth project, we only used the DLDs that we prepared and formed hydrogel networks with that. And again, we evaluated their biological activity. A lot of the work has been focused on the synthesis. And we used these three chemistries as the main, among with others, but these were the main key things to help us build the dendrimer. And I'm going to use this G3 dendrimer to just highlight how we grew this specific dendrimer. So we used FPE chemistry for the growth of the dendrimer. It's an esterification reaction where we use bis-MPa. We then used anhydride chemistry to introduce the allele functionality on our dendrimer. And lastly, to introduce the ammonium groups, we used thiolane click chemistry. And as a result, we had a dendritic family consisting of beta-alanine dendrimers. These are degradable. We have seen that they do degrade under physiological conditions. We have cysteamine dendrimers, dimethylamine dendrimers, as well as cysteamine DLDs. This is to show that we did make a lot of compounds. So we have a lot of parameters to change. And we were just it was interesting to see how, when we formed hydrogels with it, what different characteristics we were getting. I'll now move on to how we characterize in the synthesis. We use both NMR and MALDI. But starting with NMR, we use it to monitor the reaction progression, as well as see, is the reaction progressing, and also has it reached completion? Here again, I show an example of, on the left-hand side, I show an example of how we monitor the progression to make the G3 cysteamine dendrimer, whereby from the allele functional precursor, you could see the disappearance of the alkene groups and then the appearance of methylene groups. But the absolutely amazing thing about using MALDI in dendrimer synthesis is the comfort you get, or the bit of comfort you get when you see that one peak, because it's a monodispersed compound in the MALDI, which is a mass spectroscopy method. We only see one peak that corresponds to one molecular weight, which is one compound in our so it gives you that warm fuzzy feeling that you are making what you say you are. I have just also included the zoomed in versions, and yes, you do see multiple peaks there, but what I want you to focus on is the one peak before I zoom into, which I'll explain in a bit. Like I said in the first paper, it was more the screening. We saw a lot of interesting things in the first paper, but what I want to focus on or draw your attention to is a cytotoxicity measurement. But to give a bit of a background, cytotoxicity, like I said, is the evaluation of the viability of model cells towards our material or compounds. And according to an ISO, which is international, it's an ISO number. It actually says that with the same assay that we were using, a cell viability of above 70% is considered that compound or material is not considered to have a cytotoxicity potential. So that's why I've drawn a line on the 70% viability scale to show where is it cytotoxic, where is it not cytotoxic. So now going back to what we saw here is that when we had the neat dendrimers by themselves, we saw that some of them were below the line of 70, but when we incorporated them in the CNF hydrogels, we actually saw that all of the hydrogels, even though they had a high concentration of dendrimers, they were not toxic, or they were not considered toxic. Here's an example. So if we look at the G3 and the G4, the G3 you can only use up to 9 micromolar, and the G4 only up to 2 micromolar in concentration. But when you look at the cell viability in the hydrogel, we had 300 for the G4. This is more than 200 times of concentration of the dendrimer, and it was not toxic. So this got us very excited. So now I'll move on to the second project, where like as I mentioned, we evaluated the hydrolytic stability. And you might think, okay, so why? Why is it important to have a hydrolytically stable dendrimer? And the main thing is that, yes, we already have a platform of beta-alanines that we considered they do degrade. They are still amazing compounds because they are antibacterial. But as you can see in the MALDI, multiple peaks in the MALDI represent multiple degradation peaks. And at physiological conditions, this was fragmenting even after an hour. We were losing the beta-alanine functionality. The beta-alanine functionality, the one I have drawn at the top, is the one that is providing activity. Together, Holden was providing activity as long as this functionality is in place. And then when we compared it with cysteamine and dimethylamine, we actually saw that yes, these are more hydrolytically stable because we don't see the same amount of degradation peaks as for the beta-alanine. So yes, we did manage to make them. But what I do want to point out here is why was this important? You do want to have a system that is degradable because at the end of the day, you don't want these compounds to accumulate in your body, which would cause maybe other cytotoxicity effects in the long run. But at the same time, you don't want them to degrade so fast that they don't deliver their activity. And that's why it was interesting to then make another family that was a bit in between. We evaluated the cytotoxicity of these dendrimers. And the way we did this was to work out the minimum inhibitory concentration, which is the minimum amount required of your compound to stop the growth of the bacteria. We also measured the MBC, which is the minimum amount of your dendrimer or compound that is required to kill the bacteria. And the lower the numbers, the better, because then you need much less to have activity. And yes, this is a busy table, but all I want to highlight is the trends that we saw. We saw a higher activity against gram-negative bacteria than gram-positive bacteria. But overall, we had activity in all the families for most of the generations. We also saw that when you increase the dendrimer generation, you do increase the activity. And lastly, the comparison between the hydrolytically stable dendrimers and the degradable dendrimers, we saw that, yes, when we increase the hydrolytic stability, we also increase the antibacterial activity. And this is indicated by the lower numbers we see for example, the cysteamines, dimethylamine compared to the beta-alanine. And of course, like I mentioned before, it is utmost importance to measure the cytotoxicity of any compound you are considering to be antibacterial. And we saw a similar trend. When the dendrimer generation increased, we had an increased cytotoxicity, as well as the hydrolytic stability also increased the cytotoxicity. But what is important is, are your compounds active? Are your compounds toxic at the concentrations at which they're active? And here I want to show you an example of the cysteamine dendrimers. And again, it might look. Don't worry, I'm gonna walk you through it. I just want to show you that yes, even if they might be more toxic in comparison to beta-alanine, at the concentrations at which they're active, then they're actually not toxic, or they have a cell viability of above 70%. But I'll take a G2 as an example where we will compare the MBC values with the cell viability values, where we include the MVV values on the same scale. And what we see with the G2 cysteamine is that the MBC values are between 1 and 6, or somewhere around there, but these are not even considered toxic, even up to 50 micromolar. So yes, we can use them, even if we can definitely use them. Moving on to third and fourth project, where we created the hydrogels. I want to describe a bit how we did it. This is a very simple method. We have our CNF dispersion. We put it in a mold. In fact, it was actually a syringe that I cut at the top. Very simple, just to show that you can do this anywhere. You put your dispersion, you put your solution of either dendrimer or DLD, you leave it overnight, refrigerated, and in the next day, you have your hydrogel. Simple as that, no external stimuli. 2 components, and we have a hydrogel with a very high water content. So from the hydrogels that were prepared, we also, in the third paper, we measured the rheology. We wanted to find out, do we have, what kind of what kind of rheological properties do our hydrogels have when we prepare them with different dendrimers? And we did this by varying the amount of dendrimer in the hydrogel formulation. And what we saw is that at the different formulations, the hydrogels actually all behaved similarly by having the same numbers of storage modulus. But what was interesting is that at a certain ratio of CNF to dendrimer, we had reached our, say, peak storage modulus, and any more dendrimer that we add, it actually decreases the storage modulus. So here we thought, okay, do we have a system? It has a range of storage modulus. That is a good thing, but we also have an optimal amount where that is the maximum we can reach. And this is just a visual representation of just to show that these hydrogens were freestanding. We adhered them on different surfaces vertically, and they're not flowing. They are stable. They are stable hydrogels, even though they have such a high water content. We then measure the antibacterial activity of these hydrogels. In this graph, I put it here just to explain how the experiment was done. We treat our hydrogels with different concentrations of bacteria solutions. We treat the solutions with our hydrogels. We then measure the absorbance, which is given the abbreviation OD, which stands for optical density values, and we compare these values with the control solutions, which is the untreated bacteria solution and the culture medium, which doesn't have any bacteria. And what we're looking for is numbers that are same values as the culture medium for us to show activity. And again, here in the hydrogels, we saw similar trends where the gram-negative was the more preferred bacteria, even though we had activity towards both. We then also saw that, yes, when we increased the generation, we also had increased activity, and again, the hydrolytically stable dendrimers were more active. We then, from this test, we actually then wanted to confirm, are we killing the bacteria with 100% efficiency, or are we just inhibiting the bacteria? And here's just to amplify the similar trends that we've seen before, is that with the gram-negative bacteria, for example, with the G1, it killed with 100% efficiency. All the bacteria was killed with 100% efficiency, in comparison to the gram-positive bacteria, where it was the growth was inhibited, and the hydrolytically stable dendrimers did have the hydrogels with the hydrolytically stable dendrimers had a higher activity. And again, the cytotoxicity. We always have to measure the cytotoxicity of our materials. And the one thing we did see is that, yes, when it was very clear that the hydrolytically stable dendrimers containing hydrogels were, in general, had a higher cytotoxicity towards the different cell lines that we tried. But what was amazing is the G1. It had a very high activity towards all bacteria, and in the hydrogel format, the G1 cysteamine, it has no cytotoxicity. So this is a very interesting candidate that we think has a lot of potential. Now, moving on to the hydrogels prepared with the DLDs, we also evaluated their biological activity, but what we saw was that, yes, the G1 and G2, no cytotoxicity, but the G3, definitely, at the same formulation. But when we decreased the dendritic component, we saw that, yes, we actually could get a hydrogel that did not have any cytotoxicity. And what was interesting, could we then see activity in the same hydrogel? We measured it against all the bacteria in different concentrations, and we saw that, yes, it was active with E. coli, but not with the other two types of bacteria. So yeah, this might seem that, yes, okay, yeah, you're not getting the same antibacterial activity as you did in your dendrimers, but this is still a remarkable result, because using DLDs, they are known to have a lower activity towards bacteria. And compared to what is already reported, people don't even consider their DLDs antibacterial until they reach at least a generation 4 and 5. Here we are in a generation 3. So it's a much smaller, so yeah, it has a lot of potential. To conclude, I want to say that yes, we successfully made a library of both dendrimers and DLDs. We also saw that yes, the increased hydrolytic stability did enhance the antibacterial activity, but at the same time, I want to emphasize that they're not toxic at the concentrations at which they're active. We also saw that yes, we actually could make a hydrogel with over 99% water that also had that had antibacterial properties, and in some cases, when we included these dendritic polymers in the CNF network, they were not as toxic. And again, if we do have to pick a favorite, it will have to be the first generation sustaining dendrimer as well as the hydrogel as the most promising candidate. But there's always more to do, and it would be interesting to further understand the structure between the cellulose nanofibrils and the dendritic polymers. Yes, we know, or we suspect that it is electrostatic interactions, but is there something else happening here? We would be very interesting to find out. We want to know also, we've evaluated with platonic bacteria, but can we also evaluate biofilm? These are much harder bacteria to tackle, as well as bacteria that have formed a resistance. And again, the difference between beta-alanine, cysteamine, and dimethylamine, yes, they're all different ammonium groups, but how are they interacting with our biological membranes? That would be very interesting to be able to further development. And also, for the promising candidates to go further into animal studies. I would like to thank my supervisors. I would like to thank my main supervisor, Professor Malkoch, and my co-supervisor, Lars Schwarberg, and for the funding, the Knut and Alice Wallenberg Wood Science Foundation through the Wallenberg Wood Science Center, as well as the European Union Horizon 2020 Research and Innovation Program. I'd like to thank my co-authors, my collaborators, and my co-authors. Thank you for your attention.